Hi everyone. Okay, now it's working. Thank you for being here. I know it's hard to be here and listen to a talk after lunch, but we will try to not make you fall asleep. We cannot guarantee, but we will try. And my name is Emanuele, and with my colleague Yves, we are a security analyst at Compass Security, which is a company based in Switzerland. And today we are going to talk about how we were able to pawn the Synology camera BC500 for the pawn-to-own competition. So a little bit of introduction first. Some times ago, we were at a conference, like you are right now, and we were listening to a talk called Whatever Pawn-to-Own, where basically two guys were showing how they were able to pawn a router from the WAN interface and then pivot to the LAN interface and gain remote code execution. And after the conference, we discussed internally, and we decided that we wanted to try to participate to the next pawn-to-own, which was in 2023. And we didn't really know what to expect. So we still discussed, and after some discussion, we came up with a team composed by 5 people. As you can see here, it's composed by myself, my colleague Yves, and also Urs, Cyril, and Lukasz. And by the way, if you're asking yourself why I've put these images, that's because everyone in Compass has its own avatar, and these ones are ours. So if you want to just use them to fish or send phishing email to us, just feel free to use them. If you want to impersonate me, just use bad English. You don't even need the avatar, that's fine. And, but then let's talk a little bit about the pawn-to-own competition, because I'm not sure if every one of you knows what pawn-to-own competition is. So I will give you a brief introduction. The rules are quite simple. Basically, you have 10 minutes to exploit your target that you have chosen, and in total you have like 3 attempts. If you fail all the 3 attempts, basically you fail the competitions. Then no interaction is allowed. That means that your exploit should be fully automated. And the only thing that you can do is just typing the command that starts your exploit, but everything else shouldn't have any interaction. That means that while your exploit is running, you cannot reboot the target or disconnect, reconnect some cables on the target, and so on. And then the next rule is that everything should be unauthenticated, meaning that you should reach remote code execution as anonymous user. The targets will be fully set up, and all the default password will be changed. And last but important is that the targets will be fully updated with the latest available firmware from the vendor website at the time of the competition. There are different categories, and each category has its own bounty. For example, you have the NAS category, where if you are able to exploit and gain remote code execution, you will get $40,000. Then there is also the Android category, the iPhone category, and other categories, and everyone has its own bounty. And each category can have also different targets from different vendors. So for example, you can have, for the NAS category, you can have the Synology NAS and also the QNAP NAS, and you can choose one of those. Considering that it was our first attempt, we decided to choose the security camera and the printer categories, which were let's say, the easiest ones. And specifically, we chose the Synology BC500 camera and the Lexmark printer. So we bought this target, and the first one that arrived was the Synology camera. So what we did, we just opened it and connected to the available interfaces. A few days later, the printer arrived, but as you can see from the image, it was broken. So we had to ask for a replacement, and this took time because we have to ship it back, wait for a replacement to be shipped to our address. So that's why we started with the camera. So we started analyzing the camera. Now let's see how we get root access to the camera. As I said before, we just opened the camera as soon as it arrived, and we look at the motherboard for finding the available interfaces. And here you can see we identified 4 pins, and after some tests, we noticed that it was the UART interface, so we attached a USB to serial adapter and connected to it. After we found the correct configuration, for example, for the baud rate or the data bits and so on, we rebooted the camera and we noticed that in the output something that appears to be like the U-bootloader. And at some point, some kind of shell appeared, some kind of shell login appeared. So we looked online for valid credential in order to access this login interface, but we couldn't find any. But luckily for us, Synology allows you to download firmware updates. And once you download the firmware, you will download this .bin file. We analyzed it, and we realized that it's composed by different parts. You have like the header parts, where there is like the number of partitions that are inside this update. Then you have like an array of partitions, and each partition has the name of the partition and the image containing the data of the partition. And one of these was called rootfs, so you can imagine what could contain. And then as last, you have the signature to ensure that the update is not tampered when it's just installed on the camera. So we extracted the rootfs partition, and first thing we did was looking at the passwd file in order to see what kind of users were present in the camera. And as you can see here, there was like the root user and this Syno-debug user. But the root user, because of the exclamation mark, was blocked, so you cannot use it to log into the camera. Then we checked this Syno-debug user, which was not blocked and already has a password set up. So we tried cracking it, but we weren't successful, so we started some reversing, and we identified that the Syno-debug user password was updated whenever the web user password was updated. It means that the same password used for the web interface or the web user was set also for the Syno-debug user. We tested this assumption, and we tried to log in using the Syno-debug user and the web user password that we set before. And luckily for us, it was correct. So we had like a root shell on the camera. Now that we have a root shell on the camera, we wanted to see what kind of services are available or exposed by the camera. So we did the standard nmap scan for TCP and UDP ports, and we noticed that in total 4 ports were available and identified by nmap. The port 80 and 443 are basically the one responsible for the web interface that also implements all the APIs and so on. Then you have the port 554, which implements the real-time streaming protocol. And then another port on 49152, which was not recognized by nmap. After some reversing, we noticed that this implements the UPnP protocol. But since we had root access to the camera, we wanted also to see whether there was any hidden service that nmap wasn't able to recognize. So we execute netstat, and we identified one hidden service listening on port 19998 UDP. And the process responsible for parsing messages received on this port was still the WebD process, which is the same responsible for the web interface. We reversed, and we noticed that it's some kind of initialization service, meaning that if the camera is not initialized, this service can be used to help you initialize the camera. Otherwise, once it's initialized, it will reject any packet. And in our case, considering the pwn rules that all the targets will be already set up, it was useless. Then during the analysis of the Syno-debug user password change, we noticed this piece of code where it seems that the command used to change the password of the Syno-debug user was created using smprintf and then passed into the system syscall. As you can guess, the second parameter is basically the password that you enter in the web interface, so it seems to be vulnerable to a command injection. So we tested it. We tried to change the password using a simple command injection payload to create a TMP file, or a file in the TMP directory. We changed the password, that works, and also the file was present. So it means that we have some kind of authenticated password command injection. The problem is that we need unauthenticated, so we can change these with other kind of bugs, but so far it's something that we can keep for later. Then we looked also to available software that would integrate with the camera, and we noticed that on the Synology website, there was this surveillance station application that allows you to manage multiple cameras in one place, and it also supports the BC500 camera. Meaning that with this tool you can see the real-time streaming of all the cameras that you have in the network, and also change configuration and so on. So what we did, we just downloaded and installed this software on our network where the camera was attached and configured it to just connect to the camera. We then sniffed the traffic to see what kind of protocol they were using to connect to the camera, and we noticed they were using HTTP, basically plain text HTTP. So with Wireshark, we were able to see the request and the response in plain text. And as you can see from the request, there is the authorization basic header, which is sent to the camera. And as you might already know, this kind of protocol will just encode in base 64 the username and the password. Luckily for us, the username and the password that you see here are the one that you can use to log into the web interface of the camera. So if we chain everything together with the previous vulnerability I told you before, let's say that you have in your network this surveillance station connected and configured to connect to your camera, and at some point the password will be sent from the surveillance station to the Synology camera. An attacker who is connected to the same network can just sniff the traffic, steal the password, and then use it to connect to the web interface and then perform command injection and execute commands as root inside the camera. We identified that, but since it was our first phone to own, we didn't really know whether we could ask for this kind of setup. We didn't know if we could ask any specific setup or if the target should be just installed and nothing else. So we decided to keep it for later and try to identify another weakness that would be exploitable without any specific setup. And then we looked at the APIs, which were the ones that was used by the web interface. We wanted to see what kind of APIs could be called anonymously, so we used burp intruder, and we tried to connect to all the send unauthenticated requests to all the APIs we were able to find from reversing the web binary. And we identified that all these APIs allows unauthenticated requests. But GET usually it's, let's say, only used to retrieve data. So we did the same with other HTTP methods like put, post, or patch in order to see what kind of APIs would accept unauthenticated requests and maybe change some data on the camera. And here you can see that these 5 APIs seems to accept unauthenticated requests. That's great. So we analyzed each API, and basically the Activate API seems to accept only the string true. If you send anything else, it will just return an error. The Language API seems to accept any string, and the last 3 APIs always return error. We analyzed them, and we realized that the error was caused because these kind of APIs were trying to modify some files in a read-only file system. So we had to just leave them and try to find, and basically we focused on the Language API. This is a standard request. As you can see, there is like the put request with the JSON string that I told you before. And as a response, you get a standard OK. But if you look closely, you will see that the content type is application JSON. So what we did was sending a JSON object, a standard JSON object, to see how the API would react. And the API, of course, returned a 400 bad request. But if you look closely to the error, you see that only the JSON key is returned and not the full JSON. So that means that some kind of JSON parsing is implemented and maybe could be exploited. So we played a little bit more with this JSON, and we noticed some particular behaviors. Like, for example, if you send a JSON object containing a JSON key which is 52 characters long, the backend will just return a 500 internal server error. And if you send a JSON object with 48 character JSON key, you still get another error, which is the 400 bad request. But if you see in the response, you should notice some weird hex bytes that are not present in the request. So that means that some kind of memory leakage is present or could be present, and we should further analyze it. And now my colleague Yves will explain you the analysis and exploit that we created.
Yeah, thank you, Emanuele, for the introduction. And I'm going to walk you through now what we did after finding that peculiar behavior. Because if you recall from before, we saw something that would crash sometimes. We saw an error message. So that could be interesting. We saw that there were some bytes leaked. As a CTF player, that's always very interesting because that screams kind of memory corruption to me. So I really wanted to dig deeper and see what was going on there. So before we go into the nitty-gritty, low-level stuff, let's just first look at the whole request flow, how that looks like, the architecture, because that will help us better understand what's actually happening. This is our browser or curl or whatever where we send the request. And if we send a request, that's first picked up by this webd binary. That's the one that centrally takes on all the requests. It does some authentication checks, a bunch of other very strange checks that we don't have time to go into in detail. But afterwards, depending on which API you send the request to, it will forward this to one of multiple CGI binaries, so that's individual programs that will then further handle the request. It will take all the HTTP headers that you're sending initially and will forward them as environment variables. And if your request has any HTTP body, so in a post or put request, for example, it will send that as standard in to your CGI. And the CGI will then process all of this and do something with your request. So what Synology wanted is probably just parse that request and do some changes or give you back some data. But we obviously wanted to see if we could somehow abuse this to get remote code execution on that camera. So after noticing that something strange happened if you send really long JSON keys, what we did was we downloaded GDB server for ARM, we put it on the camera, and attached this to one of those Sinocam debug CGIs, and we sent that long JSON request that Emanuele showed before. And what we can observe is that it's crashing, and we have a nice backtrace where it's showing us that something was corrupted. And if you pay a little more attention, you see it's not like the webd that I mentioned before or the CGI that I mentioned before, but somehow something seems to be corrupted in libjansen. Libjansen is an external library that's used to parse JSON. So that's a dependency they use on the camera to parse the JSON that we are sending. So now that we see that something obviously seemed to have corrupted the whole stack frame and something seemed to be going wrong, it was time to actually dig into the code and see what went wrong. So libjansen is open source, it's on GitHub. So we kind of guessed which version they were using, and we downloaded that code. And at the same time, we opened it in our favorite decompiler, and we kind of started digging through it together with GDB to find out what went wrong. And after some time, we arrived at this function, this parse object function, that's used to parse the JSON object that we're sending. And at the bottom, you can see that they use scanf to take our JSON key. And they are checking if there is a space in between. And if so, they are parsing it into those two stack variables that I nicely named overflow1 and overflow2. If there's no space, it just puts everything into the first one. And for those of you that did some Pwning, some binary exploitation, you immediately see here we have like fixed size buffers, but there's no restriction on how long our JSON key can be. So if you send a really long key, C just reads that in, and we start filling those arrays and then overwriting everything on the stack, including the return address, and started to corrupt the whole program flow. Now what's kind of interesting is this scanf, that's not there in the open source code. So that's something they put in there afterwards. They modified that. We saw in some of the JSON configuration files on the device that they had some strange keys with a space in between. I'm not sure why they did that. We didn't further analyze that instead of just nesting more JSON. But yeah, so they modified the library and they introduced this nice vulnerability. This almost caused a small fight between me and my colleague because we decided where to set breakpoints to see what's going on in GDB. I had the GitHub source code open, he had the decompiled code open, and he said, oh, that's scanf, that looks interesting, set a breakpoint there. I was like, there's no freaking scanf anywhere in the code base, what are you looking at? So yeah, that's the reason why, because Synology put that in there themselves. So now that we know that we have a buffer overflow, it's time to see, can we actually exploit this? So we know we can corrupt something, but that's not necessarily enough to gain code execution. So the first thing we did was use checksec. It's a nice tool to see what protections are there on that binary. And I guess most of the CTF players will know this, but maybe for some it's new, so I'll talk about this a little bit. So the first thing we were very happy about is that there's no stack canaries. Stack canaries are a value that you put after all your buffers, and if you overwrite that, the program will abort. Exactly to prevent those kind of buffer overflows. Nicely for us, they didn't enable that. So that was very good news. Then the stack is not executable. This is something to be expected because it's not 1990 anymore. But on the other hand, it's an IoT device, so you never know. But we don't have an executable stack, so we cannot directly use shellcode. So that's like the first issue that we have to deal with later on. And then PI enable or ASLR. So each execution, the program will be loaded somewhere different in memory. We will later on see why this makes exploitation a little bit harder. So this will be the second issue that we have to deal with when we want to exploit this camera. So far so good. We were pretty optimistic that we could deal with that. That's not usually too difficult to deal with. The really annoying part was this one here that we only found out later. And that's if you read the documentation of libjansen, it tells you that it only parses the JSON if all the characters you're sending are UTF-8 compliant. What does, or valid UTF-8 characters. So what does that mean? In the simplest case, you have like a 1-byte UTF-8 character from 00 to 7F. So that's your normal ASCII range. That's easy, and that makes sense that you only have like printable characters. But for exploiting it, it will be really hard because we cannot have anything in our payload from 80 to FF, which is really difficult. The nice thing about UTF-8 is there is also 2, 3, and 4-byte combinations where some of the bytes in there can be from 00 to FF, but then you have some restriction on the previous bytes. So it's not, this will add some restrictions to us and will make it harder in the end to have a nice payload that we can use because we have not full control over all characters. So that's the third issue we have to deal with when trying to write an exploit for this camera. So yeah, next I take you through the not so short process of us trying to find and write an exploit for this. First of all, let's deal with one issue at a time. So that the stack is not executable, that will prevent like this very introductory exploitation scenario where in your payload you add your shellcode, your machine code, your assembly, you just modify the return address of that function to jump back to your shell code, and you can execute anything you want. That's maybe how some of you started with like the very easy pond problems and CTFs. And the solution is also very well known. You send your padding, you might encode some commands in there, and then instead of jumping to that shellcode directly, you modify the return address to some ROP gadget. ROP gadgets are pieces of code that are already there in the program, and you're abusing them to write your own program. So you're taking like bits and pieces of the already running software, and you try to chain them together that something nice happens. In our case, ideally, we want them at some point to point to system, and that the argument to system is like any arbitrary string that we encoded on the stacks. So we somehow have to load that into the first argument and then call system. So we're pretty confident that we can deal with that. That should be doable. So the next question is, do we really need to write a complex ROP chain? We spent quite some time trying to write a ROP chain, and it was a real pain to chain multiple gadgets, especially because of the UTF-8 restriction. And at some point, we're like, it can't be that hard. There has to be something that's easier. And luckily, there was. And that was somewhere on the stack. After the return address, there was this nice struct set up, this struct for parsing JSON. And in there was a function pointer. They used that somewhere in the processing of your JSON object. And between the overflow and the return, some other function in between would use that function pointer for further processing recursively the JSON that you sent. So the nice thing is we don't have to deal with like a full ROP chain and all of that. We can just write enough that we overwrite the return address a lot more until at some point we arrive at the function pointer. We can overwrite that with system, and nicely at that point in time, it already points to the padding that we provided because it was used to parse kind of the JSON object that it thinks is there. So for us, that made it a whole lot easier in the end to write an exploit. So I guess the key takeaway, maybe spend another 10 minutes, 5 minutes to look what's on the stack before going all in on writing your ROP chain. If you're interested in what all went wrong, you can come talk to me afterwards during the beers. So now that we've dealt with that, let's look at our next problem. That is ASLR. So on every somewhat recent system, programs are not always loaded at the same address. They're always loaded somewhere different in memory, especially to make it harder to find gadgets or to know where those gadgets are, that it's not so easy for you to write the ROP chain. So on modern computers like yours and mine, it's very hard to, because there's a lot of randomization. But we thought, well, it's a small IoT camera. Let's look at how much randomization is there. And we saw there's like 8 bits of randomization. That means if your address that you want to target is this, only those 2 nibbles, 4 and 5, are random. So what does that mean? 8 bits, there's 256 possibilities. So I know when I started out with CTFs, if I saw ASLR, I was like, I need to have a leak for this to work, otherwise there's no way. But over time, I kind of started to prefer another technique to defeat ASLR. And it's like, can we maybe just do brute forcing instead of finding another vulnerability, because that's time intensive. So let's have a look at that. If we send a request, as I told earlier, we have the webd that picks it up, and then it will start a new process with the Synology param CGI. And if we do something, if we don't hit the right address and that dies, it's not so bad. We can send a new request, and we'll just keep invoking new Synology processes, and we can keep on doing that. And that was really nice for us. Why? Because like spawning a new Synology process, that was pretty much instantaneously, that went very fast. If we crashed the webd, it would take like 10 to 20 seconds for a watchdog to realize that and to restart it, So that would not really be feasible in 10 minutes to brute force this. But with this construct, from the brute force question mark, it became more something like brute force exclamation mark. So yeah, we decided to not hunt for more vulnerability, but actually go all in on that brute forcing. And I'm going to show you how this will also solve our problem with the UTF-8 characters. That's actually quite nice. So imagine this is like the target address that we want to encode to overwrite that function pointer with. X and Y, those are the two nibbles that will be randomized, those 8 bits. So what can we do? Well, we can actually just choose them in a way that this here, in little endian form, will be a valid UTF-8 2-byte character. Should be hopefully doable. And then we just send that, and we hope that the offset in the end will match up with that. Obviously, most of the time, this won't be the case. So we will jump to somewhere where there's no code, where nothing valid is, so we'll just crash. But we just keep doing that over and over until hopefully, at some point, the actual ASLR of that process will match up with the guess that we had, and we should be able to hit that address and also have an address that's all valid UTF-8. So we kind of hope to defeat both issues at the same time. And this is the address that we came up with in the end. That's the that is system, the address of system. And yeah, as you can see, it's nicely UTF-8 encodable as 7.6 and 3.4. Those are normal ASCII ranges. They're very easy to encode. And 8.3 dB, that's the orange text on the right. You can just look at some online UTF-8 tables until you find something that's valid. So we were very happy at that point. There was one thing left. So for a CTF, I would send this, I'd be happy, I wait a few hours, and I have the flag. But because it was pwn2own, as Emanuele mentioned earlier, we had 3 attempts and 10 minutes per attempt. So was our brute force fast enough? Well, first we did some math, and we thought like with 1,000 requests, we had like 98% probability. To get over 99%, we need like 1,200 requests. That was quick napkin math. So we started to measure how long does it take for a request, and we saw it's around 100 milliseconds. So in 10 minutes, we expect to have like around 6,000 requests, times 3, 18,000. We were very confident that this should work. So we said, yes, those 2 issues solved as well. We can register for the competition. So this led us to this final payload that we came up with. All the green stuff is padding just to reach the function pointer at some point. Embedded in the padding is part of our payload. This will enable the root user that was previously locked. We'll also start telnet that we can then connect to the camera. And then finally, the encoded address of system. That was the final payload that we had to send as JSON body to the camera. Now you might ask, well, why isn't it enough to unlock the root user? We don't know the password of the root user. Well, during that brute forcing earlier on, it took us very long to discover that the password of root was 12345. So if you would enable it, it was very easy to later on log into the camera if you enable it and start telnet. So yeah, that wasn't a big hurdle to overcome. Now, that was all expectations and how we hoped it would go. Unfortunately, reality was a little bit different. So I told you it would take like 100 milliseconds roughly for a request to complete. And normally that was the case. But sometimes some of the requests would take a really long time and they would hang or time out. And if that happened, all your subsequent requests would become a lot slower. So take this as rough offsets, how long it took. And if we had multiple threads that would get stuck in some sort of hang or loop, it would get even slower. So it would slow down our brute force quite a lot. We discussed why that might be happening, and it's probably if the address that you specify and that you're calling either points to some infinite loop or points to something that wants input from you that it's never receiving. So if you jump somewhere that's valid code, but not the code that you want, this process might get stuck and it will slow down the whole camera. Because remember, this is not like your web server that you have at Google or Amazon. It's just like this small IoT device. So it's not nice if you have several of those processes stuck. So we needed some solution for that problem. Otherwise, we couldn't go to the competition. So what is like the best solution for computer scientists? Have you tried turning it off and on again? That sounds nice, but remember, we're not allowed to unplug the camera, plug it back in during competition, or do anything like that. So we would have to do that somehow remotely over the network. Luckily for us, when we were playing around with it, we noticed that if we send a really long JSON key, exactly 185 characters long, then what would happen is one of the WebD threads, so not the CGIs that would be spawned, but the actual WebD, one of those processes would get stuck. And the WebD had 10 processes where it would take on requests. And there was also a watchdog on that firmware, and it would check, is the web server still responding? And if at some point it was not responding, it would reboot the whole camera to reset it that it could function again. So that gave us the last piece of the puzzle, so we could finally put it all together. So what did we do in the end? Well, we started our brute force, very nice, with a few threads, and it just tried to hit that address. And we measured how long it would take, and if at some point we noticed that it would slow down quite a lot, we would start our reboot procedure, which meant we would just send a bunch of those long requests with a bunch of A's in them until all the thread from the WebD would hang, and the watchdog would reboot the whole camera. And once that was done, we were back to our nice 100 millisecond brute force. Obviously, it takes some time for the camera to reboot. We lose a few seconds there, but overall, this was a huge speed up than just letting it run and have that slow down. So we did some more analysis, some more testing, and we had a pretty high success rate, so we were decent confident that we could get it running in 3 attempts. So yeah, with that, we registered like a week in advance. We booked tickets from Zurich to Toronto like 5 days before the competition, so it was everything very last minute, but we were very excited to fly there. And we decided that not all 5 of us were going, but my colleague Cyril and I, we flew over. And in the flight, we had internet for messaging. So somewhere in the air, I decided to message my colleagues back home to say, hey, there's no update, right? Everything is still fine. Because remember, vendors can patch until the last minute before the competition. And then on the ground, my colleague was replying, well, actually, there's an update, minor bug fixes. So that was me in the airplane because I was like, shit, if they patched our bug, I land in Toronto in 5 hours, I pretty much can go on the next plane and fly back home. So I was stressed out for like half an hour, but they installed the update, they ran the exploit. Luckily it still worked, so they didn't catch our bug. I was very relieved. Their minor bug fix was fixing the authenticated command injection. There were like 2 or 3 of those. So a minor bug fix is like authenticated RC. That's what we discovered later on when we reversed the patch. But yeah, we were very happy that we could go to the office and demonstrate our exploit. And I made a short video of it that we don't have to wait here for 10 minutes to hopefully hit the correct offset. But you can see on the left, that's our brute force that we're starting. It will just try over and over again until we hopefully hit the correct offset at some point. On the other side, we have the camera, and you see at some point we should successfully trigger our payload, hopefully. We expanded it a little bit, that we will download a web server and then host our own code. And then here on the left, you should see that we have command in execution as root. Yeah. There's a few more slides, but thank you. So, as you can see from this tweet, we were successful. We actually were very lucky at the competition. It triggered within like 5 seconds, so I thought actually something went wrong because it was so fast, but I was very happy that it worked. If you read the tweet, you see that the bug was previously known. What do we mean with like previously known? Well, if you have multiple teams that all target the same, there will be a random drawing to decide the order they go in. There was binary factory, then synactive, and we were going third against the camera. Binary factory, the first ones that pwned it, they got the full money. Synactive got second, so the maximum they could get is 50%. They used a different bug, so they got 50%. And then it was us. And we had the same bug as binary factory, so the previously known was those 4 hours in between. Yeah, and so in the end we took home pretty much the cost of the airfare and the hotel, but still very nice experience for us. And obviously we were hooked, and like the expectation in the company suddenly were very high because we did it once, so obviously we should try again. So last year in October, Pwning happened again, this time in Cork, Ireland. And yeah, we managed to exploit another camera, this time the Ubiquiti AI Bullet. Unfortunately, the details are still just under NDA, but hopefully we will be able to talk about this very soon. So, if you like this presentation, if you want to learn more about it, we wrote a 5-part blog post where we also documented all the stuff that went wrong, all the failures. So yeah, feel free to read up there or ask us any questions. Thank you.